In this presentation, we'll solve a few example problems to illustrate some of the ideas about transfer function that we've been talking about in the previous presentations. So our first example is we'll suppose that we have the transfer function for a linear time invariant system. It's called h of s, and it's given as 3 over 2s squared plus 16. The system's input is called x of t and the output is y of t. And our goal is to find the differential equation that relates x of t to y of t. So this is an inverse problem. We have x of s going into the transfer function h of s, producing y of s. We know what h of s is, and we know that x of t is related to x of s and y of t is related to y of s via the Laplace transform. Now, one important thing we'll need in order to complete this problem is we'll need to have the assumption that there are no hidden modes. So we're seeing everything that's going on inside of this system when we give the transfer function. So here's our solution to the problem. We know that y of s is going to be equal to h of s times x of s. H of s is 3 over 2s squared plus 16, so we'll substitute that in. And then we can multiply both sides by the denominator 2s squared plus 16. And that will give us 2s squared plus 16 times y of s equals 3 times x of s. We can then distribute the terms. We'll get 2s squared y of s plus 16y of s equals 3 times x of s. And now we're ready to inverse Laplace transform this. The inverse Laplace transform of s squared y of s will be y double dot, okay? Because each s is like taking a derivative. We're dealing with a zero state problem here, so there's no initial conditions. The inverse Laplace transform of y of s is y of t. Of course, the inverse Laplace transform of x of s is x of t. So inverse Laplacing the expression here, we find 2y double dot plus 16y equals 3x. And that's the differential equation for the system governed by this transfer function. So in this last problem, you were given the transfer function, and the goal was to find the differential equation. In this next problem, you're given the input and the output in the time domain, and your goal is to find the differential equation. Again, we'll need to assume that there are no hidden modes because we're only dealing here with inputs and outputs. That is an external system description. So anything internal we can't see from just the inputs and outputs. Let's look at the specific problem. A unit step input is applied to a system that is linear time invariant. And in response, we get the output y of t equals 10 times 1 minus e to the minus 3t u of t. So we have the input, it's a unit step. We have the output, given here y of t. Now we want to find the differential equation that the system must possess. So here's our solution. We know for the zero state problem that the output and input are related in the frequency domain by y of s equals h of s times x of s. When x of t is u of t, we find that the output y of t is 10 times 1 minus e to the minus 3t u of t. So let's Laplace transform the given x of t and the given y of t. X of s then will be 1 over s, since that's the Laplace transform of the unit step. And the Laplace transform of the given y of t will be 10 over s minus 10 over s plus 3. So now we have x of s and y of s. We can now take the ratio of y of s over x of s, and that must be h of s, since h of s is the transfer function. So doing that, we'll find h of s is 30 over s plus 3. At this point, this example is just like the one we worked earlier in this presentation. We have the transfer function, and now we need to go backwards to find the differential equation. Let's do that final step. We have y of s is h of s times x of s, and h of s is 30 over s plus 3. So multiplying both sides by the denominator here, we have s plus 3 times y of s is 30 times x of s. And then it's straightforward. We take the inverse Laplace transform, and we find y dot plus 3y equals 30 times x. And that's our differential equation, and we found it from the given input and the given output. So I hope you're seeing some of the power of these methods. You can imagine an experimental condition where you would record x of t and record y of t, and then in principle you could transform those to Laplace transforms. You could then take the ratio of those, and then from that result you could derive the differential equation of the system from experimental data. When we're doing engineering, we always have to talk about units. So I briefly want to talk about the units of transfer functions. Now you remember that the units of the Laplace variable s is in radians per second because it is frequency. But what are the units of the transfer function, say g of s? It's easy to find out what they are. The units of the transfer function will be derived directly from those of the input and output signal. So for example, if we have an input x of t and an output y of t, the units of the transfer function will be the units of y divided by the units of x. It's easy to see this. Let me illustrate with an example. So let's suppose that x has units of newtons. It's a force input to the system. And y has units of meters. It's a displacement output. We can find the units of the Laplace transform of x of t, x of s. It's the integral from minus infinity to infinity of x of t e to the minus st dt. Since x of t has units of newtons and dt has units of seconds, x of s must have units of Newton seconds. By a similar logic, y of s must have units of meter seconds. Now when we find y of s over x of s, that will have units of meters per Newton. The seconds in the y of s and x of s will cancel out. So the transfer function g of s, which is y of s over x of s, must have units of meters per Newton. So you can see that we can find the units of the transfer function directly from the units of the output and the units of the input. It will always be the ratio of the output units divided by the input units.
Hey, Fitz here with TransWow, and I'm going to be talking to you today about the amazing TransWow. Takes a differential equation, boom, makes an algebraic one. Zing, then you got your output. Just like that, TransWow. You'll be saying TransWow every time.
TransWow?
Every time.
TransWow?
Every time.
TransWow.
Every time. Alright, let's move on. Let's take a closer look. Alright, so we got a differential equation right there. But in reality, who needs it? Get that out of here. Then we're going to take our TransWow.
TransWow?
Every time. Alright, this is what we're going to do. Move that guy real quick. We're going to throw down an input just right there. Wow, that is sloppy. I don't like that. Now, let's Laplace it. Whammy. Like that. Now, let's get our tranny out. You throw it right on top. Right that. Watch this. 1, 2, 3. Lift her up. Whoa! Look at that. You got your output in your frequency domain right there. Put it back down. 1, 2, 3. Lift her up. Oh! You got your output just like that. Every time, TransWow. You'll be saying TransWow every time.
TransWow?
Every time.
TransWow?
Every time.
Trans wow.
Every time. It makes your whole life better. Everything. Trans wow.
Trans wow?
Every time. Makes everything better. Kazam! Makes your whole life better. Weak in the gym. Maybe you're not worthy of that lax penny. You should change clothes or something. Maybe the shake weight's just not doing it for you. John, what do I do with my hands?
Lower. Lower. Up. Perfect.
Trans wow! Trans wow! Now you're the Hulk! Wrong Hulk! Alright, now that's what I'm talking about!
Before trans wow, I thought I wanted to be a systems engineer.
Trans wow! I can't even imagine my life without it. Thanks, Fitz.
I'm Matt, and I buy everything Fitz buys. The slap chop, the sham wow, but by far, the trans wow is the best. And all I can say is, trans wow.
Noble, what do you think about trans wow?
Trans wow!
My favorite part of Trans Wow is how easy it makes my transformations.
Meu Deus, valeu. Me traz suco cheio de amor e paixão. Que mundo maravilhoso.
Trans Wow transformed.
Meus bens. A nossa vida
Trans Wow transformed.
cheia de felicidade e amor.
Trans Wow transformed my entire life. I mean, I used to be a woman.
Before trans wow, I would never be on the lawn with him. But just look at me now. Thanks, trans wow.
Trans wow! Dr. Jones! Dr. Jones! Getting chased by a boulder? Dr. Jones! Trans wow!